We would now like to look at some very specific series circuit elements that involve capacitors, inductors, and resistors. What we're going to use here is an applet that was built by Haynes Miller in the math department at MIT. There's lots of nice mathlets that you can find online. And this particular RLC series-driven circuit is one that we'll use to illustrate various examples. So what we have here is, let's put a resistor into this circuit. So you can see we now have a resistor. And let's also put an inductor into this circuit. So now we have a circuit with two elements. And the blue here is going to represent the driving voltage. And when we add current through the circuit, you can see that the green represents the current. Now, let's analyze this circuit by beginning with talking about the equivalent impedance. So we know that for this circuit, that Z equivalent is equal to the Z of the resistor plus Z of the inductor. And that's a real number for the impedance of the resistor. But the inductor was a complex number, I omega L. And so again, we have a complex number. Again, what we need to do is we're going to write this as a modulus end of phase. And so the modulus here is just given by R squared plus omega L, quantity squared to the 1/2. And the phase, delta, is the inverse tangent of y over x. So that's omega L over R. And that's all we need to solve this circuit, because our amplitude, we know, is V0 over the modulus of the equivalent impedance. And that's easy to write down. That's V0 over R squared plus omega L, quantity squared to 1/2. And the phase of the current, phi, is equal to the inverse tangent of R delta, because delta is equal to that phase. And so that's omega L over R. So now let's look at the circuit. So if we run this circuit and we hit the time dependence, you can see that with this particular case, the blue represents the voltage and the green represents the current. And right now we have a very small inductance and reasonable sized resistance. So let's just see some limits of this expression. So in the first case, if we take the limit as R goes to 0, then the amplitude just becomes V0 over omega L. And inverse tangent of infinity is pi over 2. So the phase is just pi over 2. And that represents having no resistor, and that recovers our results for the pure inductor. So let's get rid of the resistor. And we'll change the value of L. And now you can see that the current is peaking when the voltage has reached its 0 value. That represents a phase shift of pi over 2. And again, if we run this circuit, you can see that the current is lagging the voltage, or we can say in time, the voltage peaks before the current. Now, we also can consider what happens in our actual expressions if we just increase or decrease the various parameters that are describing this circuit. Let's begin with changing, let's put some resistance back into the circuit. And let's start by seeing how these results depend on the driving frequency. So notice that the amplitude depends on omega. And if we increase omega, which is down here, we expect that the amplitude will decrease on the current. If we decrease omega, we'd expect that the amplitude of the green amplitude will increase. It's not a huge effect, but this is more, it's seen more by increasing or decreasing the inductance. So let's decrease the inductance. If we decrease the denominator, the amplitude should increase. So we can see that. If we increase L, then we expect the amplitude to decrease. There's also a subtle phase shift. If we decrease L, then this quantity goes towards 0. And as we decrease L, we're having less and less of the effect of the inductance. The phase shift is getting closer and closer to 0. And once again, let's look at how the resistance varies. If we increase R, the denominator decreases. More resistance in the circuit. We'd expect that the amplitude to decrease. And if we decrease R, less resistance in the circuit, then we'd expect the amplitude to increase, and you can see it increasing. And a subtle shift in the phase as well. So this simulation allows us to study properties of any series RLC-driven circuit.